I can shout like nobody, but that's all right. Anyway, yeah, very excited to share with you all today part of a large plan that several of us have been pursuing. This is work done with many collaborators. I've highlighted the ones who are in the audience today, each of working on a different aspect of this problem, trying to understand how the cosmic web through so-called cold streams or intergalactic filaments fuels massive galaxies at cosmic noon with fresh gas and all that that implies. So let's just kind of take a step back. This is certainly one of the first talks we've heard throughout the conference of the very large-scale structure, though we're going to have several more today. We all know that galaxies live and form in the cosmic web. This is perhaps one of the most famous images of astrophysics that are around from the Millennium Cosmological Simulation, showing an intricate network of void sheets, filaments, and nodes. Intergalactic filaments in particular are thought to hold about half the mass in the universe, so that alone is enough of a reason to want to understand their properties very well. But even if we care about galaxy formation and we kind of zoom in, this is kind of a patch of the cosmic web, and we can see how it's really tied to the locations of galaxies. You have your typical galaxies that lie within individual filaments, whereas your very massive galaxies lay at the nodes of the cosmic web and are fed by so-called cold streams or relatively narrow filaments. Now, this in particular is a somewhat interesting structure, in particular when you consider what happens in very massive halos above 10 to the 12 solar masses, where we expect the circumgalactic medium to be hot at the virial temperature, have a stable accretion shock, so the gas here is going to be at about 1,000,000 degrees Kelvin, and there's a phenomenon that at this point is quite robust, that at high redshift, above a redshift of about 2, even in these very massive halos, the cosmic web filaments that are feeding these halos, because they're so much narrower, they're so much denser than the surrounding circumgalactic gas, their cooling time is a lot shorter, and therefore they don't shock heat, they remain cold, and they're able to go all the way down to the central galaxy without ever experiencing a virial shock, and they are able to feed the growing galaxies with gas in basically a halo crossing time, which is a lot shorter than the cooling time of this T-vir gas. However, somewhat curiously, most, if not all, cosmological simulations seem to agree that below redshift of about 2, this image of cold streams feeding hot halos seems to go away. The cold streams seem to disappear. And it's not really clear why this happens, and we'll kind of come back to that a few times throughout the talk. I know a lot of you in the audience are probably thinking, well, it's AGN feedback. I'm not convinced that AGN feedback can explain this, certainly not by itself, and I hope to convince you of that throughout the talk. But just to put this in a bit more of an observational context, we saw this figure earlier this week in a talk by David Elbaz. This is work by Emanuele Dadi showing the star-forming main sequence at different like redshifts. And if you tag the stellar mass where the star-forming main sequence begins to flatten and galaxies begin to enter the green valley or begin to quench, and you convert the stellar mass into a halo mass and you plot that as a function of the redshift, at redshift about 1, 1.5 and below, this coincides roughly with 10 to the 12 solar masses, where you expect to have AGN feedback begin to kick in and a hot halo due to virial shock heating. But as you go into cosmic noon, this mass goes way up, and it's between 1 to 2 orders of magnitude larger at Z of about 3 or 4 than it is at Z of 1. And this actually works out, this resembles remarkably the early predictions for where you expect these cold streams in the hot CGM. The magenta line here dates from Deckel and Birnbaum in 2006, and I'm sure Avishai won't take offense. He and Yuval have assured me many times that this curve was really never meant to be taken too literally. This is really more of a cartoon figure, but it's remarkable how well it matches the data. This blue line we'll come back to later in the talk. This is a somewhat updated model, which you still shouldn't take too literally, as I'll convince you later. There's still a few ad hoc assumptions here, but it's certainly a lot more detailed for where you expect cold streams to still be able to survive, and it does seem to match the data. Now, I would argue that, again, these two models are both highly uncertain, but this is at least suggestive of a link between cosmic web accretion and the decline of the quenching mass during cosmic noon. The details are still uncertain, but this certainly does seem to suggest some link between the transition and the accretion mode and how galaxies begin to quench. If this was just AGN feedback should be just as important here as it is here, which is why I don't think that AGN feedback by itself really explains it. But we'll come back to that. Let's assume that streams do make it all the way to the central galaxy. I don't know how, but let's assume that they do. We expect streams to supply disks with both mass, angular momentum, and also energy for turbulence, and we heard a bit about that in the talk by Omri Ginsberg and Dhruva Chaudhuri earlier in the week. This is a movie from the Vela cosmological simulations showing 3 streams feeding a growing disk galaxy from redshift 6 down to redshift 4, and you can see how the streams really spin up the disk, and also they form these so-called violent disk instabilities in giant clumps that we heard about through driving compressive modes of turbulence, for example. So streams are not only important for supplying galaxies with mass to fuel ongoing star formation, but also they're critical in how disk galaxies in particular grow and evolve in terms of their angular momentum and their stability. What I'm showing here are observations by Chris Martin, circa 2016, on 100 kiloparsec scales, showing what appears to be some kind of a rotation pattern, or at least a shear pattern of circumgalactic gas, which at least qualitatively resembles this picture of in-spiraling cold streams that feed the disk galaxies as they grow. Talking a bit more about observations, this is a compilation of quite a few observations. This is using KCWI, Subaru, Keck, Muse, KCWI. This is the odd one out. This is using ALMA. All of these are looking in the Lyman alpha. This is specifically looking in C1, but they all show that there is a lot of cold gas on circumgalactic scales, 1, 2, 300 kiloparsec scales around massive galaxies during cosmic noon, and these qualitatively seem to resemble what we expect of cold streams flowing through the circumgalactic medium toward their growing galaxies. The reason I highlighted this, besides the fact that I was very, very fortunate to be involved in this work, was the fact that since these streams are, you can observe them in C1, these cold accretion streams are not pristine, as we so often think, but they're polluted with metals from quite high redshift. And that's, of course, expected because even though these are feeding the massive galaxies, there are small galaxies that live inside the streams, and their feedback and their outflows are going to be polluting the streams with metallicity from extremely early on. And the fact that we can see this in C1 is indicative that these streams are not only at 10 to the 4 Kelvin, but might actually host gas at like 100 degrees Kelvin that might be contributing to star formation, as we heard it talk about again earlier this week from some of the results from the FIRE group showing that very high redshift, it seems that we have molecular gas and star formation occurring in the streams, so this is at least consistent with that. On much, much larger scales, not circumgalactic streams, but really intergalactic filaments, this is a really nice observation by Umehata et al. 2019 using Muse, observing, again, a giant Lyman alpha nebula on roughly megaparsec scales. This is truly an intergalactic filament of the cosmic web, we suspect. These, at the moment, are extremely hard to observe, and you can only observe them in very biased regions that have a lot of AGN around to really boost the emission. But in about 5 years' time, Muse is going to be upgraded with a new instrument called Blue Muse, which will, number one, be at least twice as sensitive as Muse, and will also allow us to observe these things below redshift 3, all the way down to slightly below the peak of cosmic star formation, and hopefully we can really gain a much greater census of the gaseous properties of the cosmic web at the peak of galaxy formation. That's going to be very, very exciting, and really is the key motivation for trying to understand the properties of gas in cosmic web filaments in a coherent way, and that brings me to this image which I showed you before. We all care about galaxy evolution. If we didn't, we wouldn't be here. If we care about galaxy evolution, we have to care about accretion, and in particular, how streams and disks interact with each other. But in order to understand how streams and disks interact with each other, I have no choice. I have to understand how streams evolve in the CGM. If you want, that's my boundary condition. If I don't know how streams evolve in the CGM, I can't understand how they interact with disks. If I want to know how they evolve in the CGM, well, I have to know what happens when they first penetrate the virial radius or the virial shock. If I want to do that, I have to understand the properties of intergalactic filaments in the cosmic web in sheets well outside of galaxies. This is the initial boundary condition. But this is really hard to study in cosmological simulations because the resolution in the intergalactic medium in most cosmological simulations is really bad. because we tend to focus all the resolution on the growing, galaxies themselves. So you can see a series of talks next Monday, for those of you who are going to be here, about how we really tie all of this together. But now in my remaining time, I'm going to follow Allison's lead from yesterday and try and give 2 short talks about this and about this. So let's start with this, and this is work led by Samuel Liu, who's in the audience, looking at the structure and dynamics of massive high-Z cosmic web filaments. To study this, we used a novel suite of simulations that we ran a few years back. What we did basically was we took illustrious TNG 100 at redshift 2.3. We selected 2 pretty massive halos, each of which had a halo mass of 5 times 10 to the 12 at redshift 2.3, separated by about a megaparsec and connected by a filament of the cosmic web. And we zoomed in, not just on one halo or the other, but on the 2 halos plus the filament that connects them, on that whole region of the cosmic web. That's our zoom-in simulation, and our highest resolution is about 10 times better than TNG 50, allowing us to reach about 300 parsec in the cores of intergalactic filaments and about 600 parsecs in the midplane of the sheet. And this was run using the full illustrious TNG physics model. And what we did in this paper was we took this snapshot at redshift 4, and we selected 10 slices intersecting 3 large intergalactic filaments, making sure to not intersect any dark matter halos above 10 to the 10 solar masses, to really focus on intergalactic gas. And we were asking the questions, what is the thermal and the dynamical structure of the filaments, and what supports them against gravitational collapse? And I'm going to give you the final conclusion here. I won't have time to talk about all the features in this plot, but you can talk to me over coffee. This is basically we develop a 3-zone model where you have a strong accretion shock around the intergalactic filament, a cylindrical accretion shock, if you will, and an analogy of a virial accretion shock surrounding a halo. It's a cylindrical accretion shock surrounding a filament. The gas here turns out to be in virial equilibrium, and I will demonstrate that. The hot virialized gas slowly cools in an isobaric cooling flow. It passes through an intermediate regime, which is really dominated by very high vorticity and a quadrupolar vortex structure. We'll probably hear more about that today in Charlotte Welker's talk. I won't have time to discuss this today. And then at the very central region is a cold, dense isothermal core where this is basically the cold streams that we expect to feed the growing galaxies. The cold streams are not the full filament, they're only the dense isothermal core of the filament. And now let's go through this in a bit more detail. So what you see here are these 10 slices stacked together, looking at projections of the density, the temperature, and the thermal pressure. And these are the radial profiles of the 10 slices stacked together. Now, first of all, you can see here a strong accretion shock. This is what I talked about, where the temperature profile reaches a maximum, and you see a strong accretion shock in the temperature projection. And in the central region, you have a dense isothermal core, which, as we've said, represents the cold streams that are going to feed the galaxies. These are the properties, the central temperature and the central density within this isothermal core among the 10 slices. And you have a central temperature of about 2 times 10 to the 4, a central density of about 0.01 atoms per cubic centimeter, and the size of this core in this particular simulations is about 10 kpc, which is actually exactly what you expect for cold streams that are feeding 10 to the 12 solar mass halos at Z of 4, and I'll come back to that a bit later. But this indeed allows us to associate this S zone, this central zone, with the cold streams. Now, the other remarkable thing is, if I were only to show you this projection, I'm willing to bet a lot of you would have thought that this is a halo fed by cold streams rather than a stream fed by cold sheets. This vertical line here is the sheet that the intergalactic filaments lie in, and just like streams feed halos, sheets feed the filaments, and it's all very, very similar. The other thing I want you to look at is the profile of the thermal pressure is almost completely flat. That's why I said we have an isobaric cooling flow, and I'll come back to that toward the end. This is actually a very important point. What about the dark matter structure? So this is the projection of the dark matter among the 10 slices. The dark matter is a lot more extended, about 3 times more extended than the gas. And if you look in the temperature of the dark matter, what I mean like the velocity dispersion squared, right, sigma squared, it's almost exactly isothermal. And the effective temperature of the dark matter is about 10 to the 6th Kelvin, which is comparable to the shock temperature of that accretion shock that was showed in the last slide, is a lot larger than the core temperature, the core gas temperature of about 3 times 10 to the 4. That's why the gas was so much more condensed in the dark matter, and that's why the core, the cold stream, is really gas dominated, and it's not dominated by dark matter. I don't know why this keeps doing that, but I mentioned virial equilibrium. So let me convince you that the hot gas is in virial equilibrium within the cosmic Webb filament. In infinite self-gravitating cylinder, you can write out the virial theorem per unit length as being this: 2 times the kinetic energy is g times the mass per unit length of the filament. If you do this in a bit more detail, you have these 3 terms here. You have basically a volume term that contains both kinetic energy and thermal energy within the volume of the filament, a surface term containing kinetic ram pressure and thermal pressure on the boundary of the filament, and of course you have a gravitational term containing basically the gravitational potential well of the dark matter. And you can define a virial parameter in kind of the standard way, and if you plot this virial parameter as a function of the radius, that's basically the black line here. The black line is indeed reaches a value of unity just inside the shock, suggesting that in what we call the thermal zone, where you have all that hot gas, the gas is in virial equilibrium per unit length within the potential set by the dark matter filament. Not only that, look specifically at the magenta lines. The magenta lines are specifically the thermal component, so that's a metric of the temperature of the gas. The temperature of the gas is also approximately gives you in virial equilibrium. That means that the gas is at this so-called virial temperature of the dark matter filament. Now, knowing that, we can actually derive virial relations for intergalactic filaments, just like we have virial relations for dark matter halos. So you can define the virial radius of a dark matter filament as a function of the mass per unit length of the filament, the virial temperature of a filament as a function of the mass per unit length of the filament, and here we have a model for the mass per unit length of a cosmic Webb filament that is feeding a halo of mass m at redshift z. So you can tie the properties of intergalactic filaments to the halos that they feed and the redshifts that they feed them, and at least in these 10 slices that we looked at, these relations work very well. Okay, so this is a way to really understand the structure of intergalactic filaments, and this is maybe the key takeaway point from this portion of the talk. How do filaments or streams actually, or how are they able to penetrate dark matter halos? So we said that in the intergalactic medium, the cold stream is a cold core surrounded by an isobaric cooling flow in this hot virialized gas. It then begins to enter the circumgalactic medium of a massive halo, which has its own spherical accretion shock, and the pressure within the surrounding circumgalactic medium of the dark matter halo is actually much larger than the pressure of the shock-heated cylindrical gas, right? And its scales is 1 plus z to the minus 1. At redshift 4, the overpressure is about 20. So even though the cold stream doesn't feel a shock longitudinally, its surrounding gas suddenly jumps in terms of its pressure by 1 to 2 orders of magnitude, which is going to create a strong radial shock within the filament, which might cause the filament not to flow nicely and coherently down the potential well, but to fragment or to shatter into many, many, many small clouds that will proceed to disperse throughout the circumgalactic medium, creating very large covering fractions of cold gas, which could be consistent with observations by Sebastiano and his group, and Ji-Wan Yao in his talk later today will discuss this process in a bit more detail. I don't have a lot of time, so I'm not going to be able to go through most of this, but I did want to at least briefly mention a few key points about all the work we've been doing, ignoring this completely, and assuming that these are the initial conditions for cold streams and hot halos. Nice laminar flow that start out in pressure equilibrium with the CGM. That may be wrong, but that's what we've assumed. And how do streams then proceed to flow through the CGM down toward the halos? And I'm going to skip the details of this. The point is that we, under those assumptions that you have a pressure equilibrium between the cold streams and the CGM, you can define 3-dimensionless quantities that completely define this problem. That's the Mach number of the flow. So the streams flow at the virial velocity, which is about the Mach number of the halo. The second dimensionless number is the density contrast between the stream and the halo, which works out to be of order one or a few one or few hundred at redshift 2 and halos of mass 10 to the 12.5. You can derive also the expected gas density within the stream, which is about 0.01, which is consistent with what we saw in the previous simulations. And the third dimensionless number is the radius of the stream divided by the halo virial radius. That can be constrained by the cosmological accretion rate, the density, and the velocity. I'm going to skip the details, I apologize, but you also expect streams to have a radius of about 10% of the virial radius, consistent with that, 10 kpc that I mentioned at the beginning, which we saw in the other simulation. When you consider cooling, there's a fourth dimensionless number, and that fourth dimensionless number is the ratio of the cooling time in the turbulent mixing zone that forms due to Kelvin-Helmholtz instabilities at the interface of the cold stream and the hot halo. So the cooling time in that turbulent mixing zone, and the Kelvin-Helmholtz disruption time, or the shear time of the filament. And since the shear time is linearly proportional to the radius and the cooling time is like naught, this ratio of time scales can be written as a R stream divided by a critical stream like radius, which you can basically write out in this way. And if you plot R stream over R stream crit as a function of halo mass in the redshift, you see that it's almost always greater than 1, which means you're almost always in the fast cooling regime. And this line that I showed you before, right, where I said it's still a little ad hoc, this is R stream over R stream crit being greater than 20. Why 20? That seems like a weird number. Well, it's a bit of a weird number. That's why I said you shouldn't take this too literally. But it's not completely made up. I do have good reasons why it should be of order 20. And I don't have time to talk about that. You can ask me like later. But yeah, this is somewhat of an arbitrary number, still suggestive of a link between being in the slow cooling stream disruption regime and no longer and the decline of the quenching mass. I will just point out visually that when you're in the in the slow cooling regime versus the fast cooling regime, everything looks very different. In the slow cooling regime, the stream density drops quite precipitously due to Kelvin-Helmholtz instabilities. The stream really begins to shear and dilute and mix in with the CGM. In the fast cooling regime, hot CGM gas cools and condenses onto the stream and is entrained in the flow. We call this entrainment. This causes the stream to decelerate due to conservation of momentum. In fact, you can actually model m dot, which is the entrainment rate of CGM gas onto the stream. You can derive what this is supposed to scale like analytically, depending on the properties of the streams. This is a series of idealized Ramsey simulations. The point is that we know how to model entrainment of hot gas onto streams in the fast cooling regime. Therefore, we can analytically model deceleration and dissipation of kinetic and thermal energy in the stream in the background, and this leads to Lyman alpha emission from the turbulent mixing layer, which can be analytically predicted given the properties of the streams. The final, yeah, okay. I'm going to take one more minute, and I apologize, but just one more minute, John. Don't let me go for more than one more minute. This is what we get when you take these streams and you put them in a halo potential. So when you put them in a halo potential, streams become narrower as they approach the center of the halo, just because they're compressed by the profile in the background circumgalactic medium. They also accelerate inwards due to gravity. We also, in these simulations, included a UV background and self-shielding, which we hadn't included in the previous models. And when we take all this together and assume that the models we developed in the previous slide can be applied at each halocentric radius, you can derive analytically and compared to simulations, models for the flux of cold gas as a function of halocentric radius. You can see the flux goes up as you entrain more CGM gas. You bring more and more cold gas into the center of the halo, and the resulting Lyman alpha emission as a function of the radius can also be predicted analytically, and is a great match to the simulations. You can then extrapolate out what you expect the total Lyman alpha luminosity to be as a function of halo mass in the redshift, and you can get about 10 to the 43 ergs per second of Lyman alpha emission, which is consistent with observations of Lyman alpha blobs. And you can also predict, well, I'm in the interest of time, I'm going to skip this, but you can talk about the effective mass entrainment on specific star formation rate of main sequence galaxies. I'll just end with a summary and pictures, and I'll take any one question that maybe I have time for. Thank you.
Thank you so much, Nir. Sharon, would you come up and set up while we ask one quick question? All right, we have several. I'm gonna go and back there.
Thanks, Nir, for a great talk. I'm just wondering, so in your left-hand panel, you're showing that a sheet is feeding all those streams, and
Yeah.
I'm wondering what is so special about the plane of that stream. What is causing? Oh, sorry. What is so special about the plane of the sheet? Why does the sheet form in that particular plane, and instead of like feeding it from all the other directions onto the cold stream?
So, I mean, the question of why locally a cosmic sheet has any given orientation is kind of, cosmic variance, tidal torque theories, Eldovich approximation. It's just how structure formation occurred locally. But once a sheet has formed, you expect the filaments to kind of be coplanar inside the sheet, right? And just like you expect to have your low mass halos aligned along a filament and your high mass halos at the node of a few filaments, similarly for filaments, your low mass filaments will just be embedded in a single sheet, and your high mass filaments will likely be at the intersection of two sheets in a very similar way.
Thank you so much, Nir. Very interesting talk. Let's thank Nir again.